Welcome back. Here we go. We're up to electricity 8 now, parallel circuits. Start questions here. Once again, here are the instructions. If you don't get less than 7, you can't proceed to less than 8. Okay, you'll be wasting your time. Go back to where you last understood and then work through. That's the way to do it. Okay, so pause this and unpause. There we go. We should know these graphs by now. You have to learn those graphs. Nothing really tricky there. That's the way we add up resistors in the last question, and we should know what PD is in a series circuit. It's shared. Okay, so have a look at those, check those. If you're unsure, go back. All right, good. Let's move on. So I've got a little circuit I'm going to show you, which is a parallel circuit. We call it a parallel circuit because when you draw it as a circuit diagram, it sort of looks parallel. Here we go. There we go. So here's a parallel circuit. We've got a cell up here, and that cell is actually giving out 24 volts. It's quite a big, powerful cell. And we've got 2 lamps here. Okay, and notice that the current leaves this cell, and when it gets to this point here, it actually has a choice. It can go both ways. So some of the current goes this way, and some goes this way. And if we follow the current all the way back around that, what happens here? They rejoin. And so in a parallel circuit, one of the things that happens is that current can split up at a junction. We call that a junction, and it can rejoin at a junction. So if I was to check the current with this neat little current meter thing here, look, if I put it on there, 4 amps is leaving the cell. 4 amps, 4 amps, 4 amps, 4 amps, 4 amps, 4 amps. And then 2 amps goes down this branch, 2 amps goes down that branch. And here we go. They meet back up again at the junction. There we go. And 4 amps flows back into the cell. Okay, so whatever leaves the cell goes back in, because current is this physical thing. It's a real thing. Okay. Now, the main difference between series and parallel circuits is that in a parallel circuit, each component that's connected in parallel gets the full voltage. So let me show you. So this cell, or battery of cells, is a 24 volt cell. Now if I connect the voltmeter across here and across this one, this lamp here gets 24 volts and this lamp here gets 24 volts. Okay, and that has some advantages, because in real life it means both of these lamps would be bright. If they were connected in series, they would share that 24 volts, and so they'd only get 12 each. They wouldn't be as bright. Okay. Another thing about parallel circuits that you already know about, if I break the circuit here, let's just break that circuit. There we go. This lamp is unaffected. That lamp is still getting 24 volts, look, and it's still getting 2 amps of current. Okay. So this is some of the advantages of a parallel circuit. Okay, so that's basic stuff there. So getting back to our PowerPoint, let's have a look. Let's move on. So why does each component get the whole voltage? So here we go. I've got a cell, and you can see there that the potential difference across the cell is 1.5 volts. It's connected like that, look. Let's add another cell. Okay. Now this cell thinks it's connected to that battery all on its own, and it also gets 1.5 volts PD, because this side is connected all the way to there, look. Okay, so both of them have a potential difference across them of 1.5. They're both connected right to the ends of the battery. And if you look at the left picture there, that's actually a circuit diagram. If I take that lamp out, the other lamp is unaffected. This lamp down here doesn't even know of its existence. Okay, as far as it's concerned, it's just connected to 1.5 volts there and 0 there. So that's why this parallel circuit works like that. Okay. Now here we go. Can't escape from this. We need to be able to be applying the formula Ohm's law of V equals IR. So I'll go through this one. So let's look at our circuit there, and we have a cell, 1.5 volts. We have a lamp with a resistance of this 0.75, and we have a lamp with a resistance of this 1.5. Okay. And the first question is, what is the current flowing through the 3 ohm lamp? I'm sure I've made a mistake there. Let's have a look. That should say 0.75 ohm lamp. Okay, I do apologize. I won't stop recording. That should say 0.75. I'll change it in the PowerPoint files. Okay, so can we see what we've done there? We know the resistance, we know the voltage, we use I equals V over R, 1.5 volts divided by the resistance, and then that tells us, look, that 2 amps is flowing through this current. Okay, can we do the same for the next one? I bet you've already done it. There we go. Do the same for that one, and can we see I've added to the diagram there, we've got 1 amp flowing there. So the next question, you should all be shouting at me that 3 amps must be leaving the cell, because we can see that it's split off, going 2 and then 1. And you'll all be screaming at me now, because you know this, that 1 amp will be, sorry, 3 amps will be flowing back into there. Okay. Do you get that? Pause it, think about it, go back. Okay. So, in general, we can say this. I've replaced that picture there with 3 light bulbs. I've said that the current leaving this cell is called current 1 or I1, and then a current I2 flows down there, a current I3 flows down there, and so on. Okay, and I know this little formula at the bottom here, look, that the current that leaves the cell must be equal to all these 3 there. Okay, and they obviously all join back up and come back into the cell. So each component gets the same potential difference or voltage, and the total current is that. Okay, that's a basic note. Okay. Do you get that? Let's move on. So here's a question. Try solving this. Pause the video now. And I'm unpausing, so let's have a look. What is the voltage across each lamp? Well, that's easy. They're all connected in parallel, so they all get 12 volts. They get the full 12 volts. What is the current through the 6 ohm resistor? You can do that. You know the resistance, you know the voltage. The current is voltage divided by resistance. Are we okay with that? What current flows through the 12 ohm resistor? We do the same thing again. We know the voltage, we know the resistance, and we get 1 amp. So what is the current I3? Now we can do this now. We don't need to do any more sums, because we know the total current here, look, leaving is 5, and we know these are the 2, so we can just work it out. It's 2 amps, because it's going to be 2 plus 2 plus 1 makes 5. And so what is the resistance of this middle lamp? Once again, we are applying that formula. We know the voltage, we know the potential difference, we know the current. This time we're rearranging like that. Okay. So get used to using these formulas. If you're going to get anything higher level, intermediate to high level, you've got to be able to use the V equals IR formula and apply it. Okay. So here's a question. What is the total resistance of this circuit? Pause, have a think. Now the way to think about this, right, I'm ignoring the whole of that circuit. Okay, all that bottom bit, I'm ignoring it, because I've got a cell that's supplying 12 volts and it's giving out 5 amps. And I know that resistance equals voltage divided by current. I've got 12 volts, 5 amps. So therefore the resistance is 2.4 ohms. Okay, now that's pretty weird, look, because when we add up the resistances of all these things in parallel, they add up to less than adding them up just like normally. Okay, now that's quite weird. That's quite a high level sort of thing to get your head around, but the total resistance is actually less. So how do we explain that? Okay, remember our model of current flowing through a conductor. We have the ions, the atoms that are vibrating, wobbling, and they are bumping into the electrons and resisting the flow. Okay. Now, if we connected 2 resistances or 2 lamps with resistance in series like this, look, here you go. what we're doing is this, look, we've basically made one long resistor. And if you think about it, if the current's got to try and fight its way through twice as far, then it's twice as difficult. So the resistance actually doubles, okay? And you add these resistors up. Look at the situation in parallel. The current comes to a junction. It can go that way and it can go that way, okay? It can go up through here or down through here. And the effect of that is that it makes the diameter of the conductor bigger. So there's more space, there's more room for a current to get through. Okay, so that's why it happens. So if we add resistors in parallel, the total resistance gets less. You're giving a bigger path for the current to flow through. When we add them like this, we're making a longer path for them to go through, and so they will get more resistance. Okay. Now, you may notice that the connecting wires are these little red wires and green wires. Okay, connecting wires have a very, very low resistance. Okay, so that's why I've not included them in this particle model. I'm just looking at the resistors because connecting wires have a very, very low resistance. Okay, that's why we use them to connect stuff, and they're made out of copper, which is a very good conductor. So have a think about that. This is quite high level stuff. This is bordering on higher tier, and this is getting into A-level types of explanation, but it might help you understand why. Okay. Now you've seen some of the examples. Go back through the examples and have a go at these questions. Okay. You may notice I've put there important draw circuit diagrams. Okay. Have a go. The answers will come up in a second, but you really exhaust yourself. Go back and watch again. We talk about these parallel circuits and about resistance and the current going through the circuit and so on. Okay. And I'm going to pause now. And I'm coming back with the answers. Okay, so here are answers. Now, check them. Any issues, get a hold of me on Teams. Oh, and there's a little quiz to finish up with. Now, you may see some of these before, actually. So let's have a look. Let's start it. Unit of resistance. Ohms. Good. Next one. What causes resistance? Is it that one? Yes, electrons colliding with metal ions or metal atoms. Next one. How do we calculate resistance? You should know by now. It's that one. Next. Oh, I have to think about this. Does it mean it's got a lower resistance? I think it means it's got a lower resistance. Okay, go back a few lessons because that was in there somewhere. The bulb. Okay, next one. I can't hear you shouting the answer. The colour of the wire doesn't affect. Okay, next one. Oh, 230 ohms in series. We add them up, so that must be 60. Think about this one. If we had two 20 ohms in parallel, what's your answer going to be? Can't be that one. Can't be that one. It's not going to be 0. It must be 10, okay? Because they add up to be less than the sum of the resistors. Number 9. Ooh, that's going to be a diode. Go back to your diode lesson. And the final one. Yeah, you got it. Thermistor. Good. Good. So a lot to get your head around there. Okay. Go back, review it again and again and again. If you're really stuck, come and see me for the answers. Okay. Thank you. Bye-bye now.